for exam 4, chapter 6, thermochemistry. Start with number 2. What's the kinetic energy of a 1.56 kilogram object? And there's the mass. And traveling at 94 kilometers per hour. Okay, what's the formula for kinetic energy? It should be in the useful information too. One-half mass times velocity. But if these units are going to be in joules, mass has to be in kilograms, and velocity has to be in meters per second. Right? Mass is already there. Right, that's good. This has to be converted to meters per second. Remember how to do that? You've got 2 units of measure that need to change. Right, length and time. So we do them one at a time. Well, I'm going to change the kilometers first. Kilometers to meters, right? This is in the numerator, that's in the denominator. So 1 kilometer is 1,000 meters. Okay, meters are taken care of. Now we can do hours. So hours on top, since this is on the bottom, seconds on the bottom where it needs to be. Does anybody know how many seconds in an hour?
Right.
60 seconds in a minute.
Yeah.
60 minutes in an hour.
60 minutes.
So 60 times 60 is
30,000.
right. There you go.
It took me a second.
There we go. Okay, so we'll crunch those numbers and get a speed in meters per second. 94 times 1,000 and divided by 3,600. Yep. So that's 26.1 meters per second. Now we can substitute in the formula. And the units will come out as joules. 1/2 mass times velocity squared. Okay. So let's square that number. 26.1 squared, I get 681 times 1.56, and then take half of that. I get 3 significant figures. 531 joules. Okay. Now, that means that a joule is equal to kilogram meters squared per second squared. They're equivalent. A joule is that. Because we had kilograms times meters squared per second squared. Okay. Is that on there? What did I do wrong? Hold on a second. 1.56 kilograms, 94 kilometers per hour. Should be right. Yeah, 26.1. 6.1 squared. Yeah. And here, 10 times 1.56 divided by 2. Yeah, 531 joules. That's not there. It says kilojoules. Okay, what's a kilojoule? A kilojoule is 1,000 joules. So that means we would have to move this, which direction? The unit's getting bigger, so the number gets smaller. That means we have to go, yeah. 0.531 kilojoules. There we go. Which is, the nearest one we can find is A. 5.32 times 10 to the minus 1 kilojoules. That would be scientific notation.
And you always have the 10 to the minus for the most part on these answers.
Not necessarily,
Okay.
yeah. And especially if it's a number that's manageable. It just depends on the test question. Yeah. All right. Okay, who's that? Scroll. Wyatt. Okay, we got 4 Zoomers. I hope you Zoomers are coming to lab. It'd be a shame if you missed lab today. Number 3. Which of the following statements correctly describes the signs of Q and W for the following exothermic process? Okay. Water gas going to water liquid. Water gas goes to water liquid, and it tells us this is exothermic. We could probably deduce that from the conditions. Because when you condense a gas into a liquid, you have to give up heat. But they're nice. Okay. Pressure is 1 atmosphere. We may need that, we may not. And temperature is 370 K. Which is 100 degrees. Not quite 100 degrees. You subtract 273 from that, and you get less than 100. So this is happening just below the boiling point at 1 atmosphere. Okay, so compare Q and W. Q and W. Okay, let's draw a picture. If this is a container and we got a piston in it with 1 atmosphere pressure on top, and it's filled with water gas, and that water condenses into this pool of water liquid. Okay. If we're going to maintain that pressure, then what's going to happen to that piston? It's going to drop, right? So volume is going to go negative. Work is minus pressure times change in volume. Okay. So if the change in volume is final minus initial, small minus large, this is going to be negative. Okay. And the pressure is constant. So negative times negative is that. So this work is positive, which means work is being done on the system. This is our system. That makes sense? Okay. So work is always positive. How about Q? Well, if it's exothermic, Q is negative. It gives up heat. Right? The system is losing heat. So W is positive, Q is negative. Which one suits that one? Q is negative, W is positive, C. C works. Okay. I would have had trouble figuring this out if I didn't draw a picture. I have to have pictures sometimes. Some people can do it without pictures. I'm not one of them. Okay, that was 3. Let's see, what about 7? 1 mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters. So the initial volume is 1 liter. The final volume is 8.93 liters. Okay. Against a constant pressure of 1 atmosphere. So pressure is 1 atmosphere. How much work in joules is performed on the surroundings? Is that actually what's happening? If we have it down here at 1 liter and it expands, yep, expands to a total of 8.93 liters. Yeah, it's doing work on the surroundings as the gas expands against a constant pressure of 1 atmosphere. Okay. And we need a conversion factor because if we calculate work as minus P delta V, then we've got 8.93 final minus initial, 1 atmosphere, times 8.93 minus 1. So that would be a positive and a negative. So that would be 7.93 times 1. But this is liter atmospheres. We need a conversion factor for joules. And I think it's given there. 101.3 joule per liter atmosphere. There we go. 8 times 100 is 800, so it's a little less than 800, I think. Oh no, because this is more than 100. So it'll be around 800. Closest one to that is negative 803. Trying to save time on a test. You can estimate those things and look for the answer, save a lot of time. Can't always do that, but in this case, these simple problems, sometimes you can. Okay. 7, scroll down to 12. Calculate the work associated with the compression of gas from 121 liters to 80 liters at a constant pressure of 13.1 atmospheres. Okay, so we're doing again from 121 to 80. Right? This is initial, and this is final. Right? So we're going to have our work again is negative. Oh, pressure. I put everything out here first. 13.1 atmospheres. So pressure is 13.1 atmosphere. And then the volume change term is final minus initial. So that's 80 minus 121. Okay. That's a minus 41 here times 13.1. Actually, a negative 13.1. Well, that's a positive 537 liter atmospheres. Okay. And the hint there, I mean, you can tell from the calculations that this is work being done on the system because it's positive. But no, it doesn't tell you. Now, you have to deduce that from it. So this is positive. So it wouldn't be A. I'd go the other direction. It would have to be B. It's positive 537. Okay, scroll. 14 through 17 is based upon this situation. Consider a gas in a 1 liter bulb at standard temperature and pressure connected to an evacuated bulb. Doesn't say how big it is. Really doesn't matter. So this is 14 through 17. Okay, so we got a 1 liter bulb connected by a valve to another one. This is a vacuum. And this is at standard temperature and pressure. So I'm not sure what they mean. I think now we've switched to standard temperature is 25 degrees. When we were talking about gases, it was all 0 degrees. But I don't think it's going to affect the outcome. In 1 atmosphere, that hasn't changed. Okay, so that's the starting situation. What happens when the valve is open? Right, we know the gas is going to and equalize pressure in there. Right. And if we knew the size of that bulb, we could calculate what it would be. Right, we've done that before. But we're looking for an answer to this question. What? 14 is Q, 15 is W, 16 is internal energy, and 17 is enthalpy. Okay, so let me reread that to be sure. Consider gases STP is connection with the energy. Now, it doesn't say that it's maintained at standard temperature. We know the pressure is going to drop and the temperature is going to drop unless we say this is an isothermic situation. Let's see what it does to our outcome. Delta internal energy is Q plus W. So if we find out what these are, then we can answer this one. And if we find out what this is, I am assuming, based upon this question, when they say at standard temperature and pressure, it stays standard temperature and pressure the whole way. So in other words, there is a way to maintain the temperature when the valve is open. If there's no change in temperature, then Q doesn't change, right? Q has to be constant. And working requires that there be a resistance of some kind. When you open that valve, it's just going, there's nothing pushing back. Right, it's forced through a distance. And there's no force being applied to get it there. So work is 0. Actually, I should say this. Q is equal to 0. There's no heat transfer. There's no work being done. There's no change in internal energy. And enthalpy is related to Q if the pressure is constant. They're identical, but since Q is 0, then it doesn't matter what happens to the pressure. I mean, enthalpy has to be 0. There's no alternative. Okay, so they're all 0 in this scenario. Is everybody thoroughly confused now? Okay. I need a drink. So 18. I'll go ahead and put 18 up here and erase them all at once. Okay. I think I left those bolded just to emphasize which is which. Energy, work, enthalpy, and heat. Energy, work, enthalpy, and heat. Okay. Which ones of these are state functions and which are path functions? This is a path. This is a path. This is a state. And this is a state. So the capital letters are states and the small letters are path functions. So to answer this question, how many are state functions? 2 of them. 2 of those given are state functions. The other 2 are path functions. All right, so I'll erase this and get ready for 19. Let's see, which of the following properties is or are intensive properties? All right, we've got 4, 5. So this one is energy, concentration, volume, temperature, and mass. We're looking for intensive properties. So an intensive property doesn't change with the amount of substance, right? Mass changes with the amount of substance, right? You have more substance, as long as it's the same substance, you have a change in mass. So that's not an intensive property. Temperature is intensive. If I have an iron ball at 20 degrees, well, let's make it hotter, 90 degrees, and then I have a small iron ball, isn't 90 degrees, right? There's the difference in mass, but they're the same temperature. So this is an intensive property, okay? Amount of substance changes, volume changes. That's an extensive property. Concentration, most ratios can be considered intensive properties. Like density, mass per unit volume. Concentration, moles per liter. That's an intensive property. Energy is extensive. It depends on how much you have in your system as to what the energy content is. Yeah. So there are only 2, temperature and concentration. Which should be C. C gives you those. Roman numeral 2 and 4. Let's see, 23. Consider this reaction. We're going to burn ethanol. Seems like a waste, doesn't it? With that equation, we're combusting ethanol and oxygen, and the delta H is minus 1.37 times 10 to the 3rd kilojoules. What about these propositions? The reaction is endothermic, exothermic. The enthalpy term would be different in the water form. If the water form, I got things in the way. If the water form was gaseous, which of these properties is true? Okay, so we can have more than one true. Well, based upon the delta H is negative, that's exothermic, right? So that means Roman numeral 2 is true. How about the last one. The enthalpy term would be different if the water formed was gaseous. Notice the water is liquid form. If it were gaseous form, more of that heat would be retained in the gas, because we know what happens when a gas condenses. It gives up heat. Well, if it's still in the gaseous form, it's got some of that heat retained, right? So the enthalpy term would be a little bit less negative, right? 1.2 maybe instead of 1.37. So yeah, it would change if the water form was gaseous. So Roman numeral 2 and 3, E, would be the best answer for this one. It's kind of tricky, right? You have to stop and think about it. We generally think of enthalpy as simply chemical reaction, right? But there are terms of enthalpy terms for phase changes, for solutions. We're going to do those today. We're going to do the heats of solution for sodium carbonate, sodium bicarbonate, and what else? Oh, acid-base reaction. And then the fourth one is the one we do first for calculating calorimetry constant. All right. So that one's E. How about 24? How much heat is required to raise the temperature of 5.75 gram sample of iron? The mass is 5.75 grams of iron. We'll just stick that in there for giggles. Specific heat of 0.450. Specific heat of iron then is 0.450 joules per gram degree C. And we want to know how much heat is required to raise its temperature from 25 to 79. So the initial temperature is 25 degrees C, and the final temperature is 79.8. Okay, remember the formula? Q equals specific heat times mass times change in temperature. Okay. So we just have to be sure we put them in the right place. Calculation is going to be 0.450 joules per gram degree C times mass 5.75 grams. So that cancels the grams. And then the change in temperature is final minus initial. So 79.8 minus 25.0 degrees C. And that cancels degrees C, leaves us with joules only, which is the unit for Q. And if we do our calculations correctly, in the interest of saving time, we should get 142 joules. Okay, that's the amount of heat required to do that process. Okay. That was just a warm up for the next one, which is a lot more complicated. 26. 32.5 gram piece of aluminum with a molar heat capacity of 24.03 joules per degree C mole. Instead of grams degree C, now it's mole degree C. Heated to 82.4 degrees and dropped into a calorimeter containing water. And there's its specific heat. Initially at 22.3 degrees. Final temperature is 24.2. Ignoring the significant figures, calculate the mass of water in the calorimeter. There's one other factor we have to ignore also. Well, it wasn't given to us either. Is the calorimeter. What effect does the calorimeter have on this process? We have to assume it's ideal, has no effect. So in this case, let's put what we know up here, 32.5 gram aluminum. So mass of aluminum is 32.5 grams. With a molar heat capacity of 24.03. So S for aluminum is, what did I say, 24.03 joules per degree C mole. And its initial temperature is 82.4. So the temperature of aluminum is 82.4 degrees C. And water is, mass of the water is unknown. That's what we're searching for. But we do know the specific heat of water is 4.184, is it? They only use 2, okay, 18. I'll stick to this one because if I don't, then there could be a rounding error and it wouldn't be up there. Joules per gram degree C. Because they're looking for mass of water, we use this one. The gram associated specific heat. Initially at 22. So the temperature of the water is 22.3. There we go. Final temperature. All right, is that the final temperature for the water or for the aluminum? How about both? You put them together in that, once they come to equilibrium, they're both at the same temperature. So you measure the temperature of the water, you got the temperature of both of them. So the final temperature is the final temperature for both the metal and the water. 24.2 degrees C. Now that's everything we're given. And what we need to do is set up the formula with all its terms. And remember, in a calorimeter, this is an isolated system. There is no heat transfer between the system and the surroundings. So everything that happens in that calorimeter must add up to 0. There's no change inside the calorimeter. So 0 equals the heat change for the aluminum plus the heat change for the water. Now, if we knew what the calorimeter constant was and we're given values, we'd put another term in there for the calorimeter, which is what you guys are going to do for our experiment. But to answer this question, that's all we need. All right, so what's the expression for the Q of aluminum? Well, it's going to be the specific heat. I'll just do it all. Specific heat of aluminum, right? Times the moles of aluminum, right? Because this is in molar heat capacity. Times the change in temperature for aluminum. And then plus S for water, and then mass of water, times its heat change. Okay, we know we're going to need moles, so let's change this to moles. Grams, mole. But what's aluminum? Let's see, aluminum, 2698. Okay, let's find out how many moles of aluminum we got. Should be a little more than 1. 1.09, 1.091 moles. Okay. So 0 equals this specific heat capacity for aluminum, 24.03 joules per degree C mole. Moles of aluminum, 1.091. And then change in temperature, final minus initial. Final is 24.2. Minus its initial, 82.4 degrees C. So we know this term is going to be negative, because that's a big negative minus a well, minus a big negative and a positive small. So that's going to be the negative term. Then for water, 4.18 joules per gram degree C. Then the mass of the water is our unknown. And its change in temperature is also final, 24.2, minus its initial, which is 22.3. Okay. So that's all the thinking. The rest is just crunching numbers. So I'd calculate this one, then take this one times that one, and that would be a term preceding the mass of water. Then I take this one, change its sign, and divide it by the term that's in front of the mass. There you go. We need to do that. Maybe we can do this one, and then if get any more like that, I'll just set them up and we'll let it fly. Because we're going to run out of time anyhow. Okay, so 24.2 minus 82.4 is 58.2, negative 58.2 times 1.091 times 24.83. And that's a negative. I'm going to keep this in standard notation. 1,525.8. Now, what are the units here? That canceled. This canceled. This is joules. This one is 24.2 minus 22.3, a positive 19. 1.9, excuse me, 1.9 times 4.18. And that's 7.942 times the mass of water. Okay, so I'll bring this on this side, makes it positive. That's 7.942 times the mass of water. And then the mass of water is going to be this number divided by that number. Just checking, it's already in my calculator. There we go. So I get 192 grams. It's not up there. Why is it not up there?
On your
I do
goals
moles.
for the aluminum.
Yeah.
You have 1.091, and in our review it says 1.205.
Ooh. 32 point, let's see, did I read that right? 32.5 and 26.98. Yep. Oh, I don't know where I got that one. You're right. 205. So we have to change it wherever it occurs. Here. Okay, that'll change this one. This one. Definitely that one. Let's do it again. 4.2, 82.4, 1.205, and 24.03. So that's minus 1,685.2. Now divide that by 7.42. That's 212. There you go. Get bummed out with math. Okay. Let's see. 27. 45.9 gram sample of metal is heated and then placed in a calorimeter containing 100 grams of water. The final temperature of the water is, which metal was used? All right. Okay, so the temperature of the metal is 95.2 degrees C. Yeah. Okay, everybody's still there. Testing. Okay, we're getting feedback. Let's see, 1, 2, 3, 4. Everybody's still here. That's good. But I'm gonna have to reshare the document. Which is right here. It's still on. Here it is, still on 27. Okay, then placed in a calorimeter containing 120 grams of water. The mass of the water was 120.0 grams. And specific heat of the water was 4 point, we're still only using 3 joules per gram degree C. And what else we given? The water starts at 21.6. So initial temperature of the water is 21.6 degrees C. Final temperature is 24.5. Okay, that's all of our data right there. How are we going to identify the metal? By its specific heat. Okay. So again, we set it up like this. Q of the metal plus Q of water. Q of the metal is going to be the specific heat of the metal, which is unknown, times the mass of the metal, 45.9 grams, times the change in temperature. Final temperature is 24.5 minus the initial temperature, which is 95.2 degrees C. Then we do it for water, which is 4.18 joules per gram degree C. And then the mass of the water is 120 grams. Checking my units, same units. Yeah, okay. And then change in temperature. So the final temperature is the same, both of them, minus the initial for water, 21.6. Okay. Now all we have to do is resolve that and find out what the specific heat for our metal is. And it should be 0.45 joules per gram degree C. And that would be iron. So iron has about 1/4 of the specific heat capacity of water. In other words, put the same amount of heat into water as you do into the iron, and the iron will get a lot hotter. So if water weren't a liquid, it'd make a good heat shield on a space capsule. But instead, well, some reentry vehicles still use ablative heat shields. In other words, they get so hot that the material melts and sloughs off, takes the heat with it. So those heat shields have to be changed every time you use that capsule. The ceramic heat shields are meant to not transfer heat across themselves into the material underneath. So what they do is they get hot, they got very, very low heat capacity. So they get really, really hot and they transfer that heat to the air and the air flies off. In fact, it ionizes. That's why for several minutes when a capsule is re-entering the Earth's atmosphere, you can't communicate with it because there's an ion shroud around it, interrupting communications. Okay, so that's 27. All right, 28. Let's see, you have 295.5 grams of a solid at 30 degrees and let it melt in 425 grams of water. The water temperature decreases from 85.1 to 30. Calculate the heat of fusion of this solid. Okay, let's put what we've got up here. It's hard to see like that. I need another marker. Um, 295.5 gram solid mass. 295.5 grams solid at 30 degrees is the temperature of the solid is 30 degrees. Okay. And let it melt in 425 grams of water. The mass of the water is 425 grams. And the initial temperature of the water is 85.1 degrees. Temperature of the water is 85.1 degrees C. And the final temperature is 30 degrees. Okay, that's important. Here's why. If the temperature of the solid, if it melts and then the temperature of the liquid changes, then we've got two factors. We don't have just the heat of fusion, which is the amount of heat required to melt a gram of solid. You've also got the specific heat factor. So since it's at 30 degrees, then all we have to do is say, all right, how much heat was transferred from the water? And let's see, 425 grams. Let's see, Q of the water. 425 grams. Let's see, I need specific heat too. 4.18 joules per gram degree C times its temperature change. The water changes from 85.1 to 30. So it's 30 minus 85.1 degrees C. That means the water is losing heat. It's a negative value. The reason I'm doing this in two steps instead of putting it in one formula is because I think it makes more sense this way. It's intuitively. 85.1. So that's minus 55 degrees, right? Yeah, minus 55.1 degrees times 4.18 times 425. So this is minus 97885 joules. 1, 2, 3, 4. Yep. So that's how much heat was lost by the water. Where did it go? It went into the solid, the mass of the solid. Well, heats of fusion have units of joules per gram because they take place at constant temperature. temperature is not a factor, right? Let's see, this is the first semester. Second semester, we'll start off talking about phase changes. But take my word for it now. When something melts, the temperature is constant until it finishes melting. That's why I tell you at the very beginning of the labs, put ice in water, and as long as you've got ice and water together, the temperature is constant because the melting takes place at a constant temperature. So we don't have a temperature factor in there. What we need is heat divided by the number of grams. So that's 97. Actually, into the object would be a positive. This is leaving the water. This is going into the object. And for each gram, 295.5 grams. So I just changed that sign divided by 295 point, oops. 295.5. There we go. So that's 331 joules per gram. Okay. We probably could have put this into a 0 equals Q plus Q, and it would work, right? But I think explaining it in these terms probably makes more sense. Okay, 32. Give it a little time. Where's I'm running? So I have to finish it after the lab. Okay. In a lab, you mix two solutions, each originally at the same temperature, and the temperature of the resulting solution decreases. Okay. Inside our calorimeter, that's what we're going to do with heats of solution. We're going to, one of those materials we put in water, the temperature is going to drop. The other one, the temperature is going to go up. So we can say if the temperature drops, the process is endothermic because it sucks heat from that isolated system in order to cause the solution to occur. So which is the following true? The chemical reaction is releasing energy. No, it's absorbing energy. The energy released is equal to S times M times delta T. Oh, energy released. No. That's the key term. Released. It's not released. The chemical reaction is absorbing energy. There you go. Since E is more than one of these, we have to look at D. The chemical reaction is exothermic. No. So C is the only good one there because this reaction is, this solution is an endothermic process. 36. Exactly, 123.7 joules will raise the temperature of 10 grams of metal from 25 to 60 degrees C. What's the specific heat capacity of that metal? I don't even know if we need to do this one. I mean, just all you have to do is look at the units of measure, joules per gram degree C. You just take the heat, 123.7 joules. What's its mass? 10 grams. What's the temperature change? It went from 25 to 60. So that's 35 degrees change. Just divide those out, right? And you should get 0.34353 joules per gram degree C. So does that make any sense? This is about 350. Yeah, 100 over 300 would be about a third. That looks good. 38. Okay. On a cold winter day, a steel metal fence post feels colder than a wooden fence post of identical size because. All right. Let's look at this. Steel versus wood. So if this is a steel fence post, I'm going to use Fe for iron. And this is wood. Okay. And you touch this one with your hand. I'm not going to draw a hand. I never was good at that anyway. If you touch this one, it feels colder than that one, and they're at the same temperature, right? Temperature of this one equals temperature of that one. Right? This one feels colder. In fact, that's the one you don't want to try to touch with your tongue. Like everybody's seen Dumb and Dumber. Yeah, don't do that. Or World's Dumbest something or other. Right? I think they had one of those one time. Okay. Let's look at the answers. A and B have to do with comparisons of heat capacity. C says something about resisting temperature change. Mass of the steel is less than wood, so it loses heat faster. Well, that doesn't make any sense at all. Two of the above statements are true. All right. I would focus on specific heat. If this is the heat content of this iron, say they're the same mass. The heat content of the steel post is equal to its specific heat times mass times change in temperature. And this one is the wood and its specific heat and mass and change in temperature. Okay. If they're the same mass, then we can discount this term. Right? They're going to be the same mass. Let's see, can we ratios those? If this one feels colder, what does that mean? That means heat is being transferred more efficiently, right? More heat is leaving your hand to this one. So we could look at it two ways. Say if the temperature of the wood and the iron were to change the same amount, and they're the same mass, then the only difference between the two would be their specific heats. And if we transferred more heat out of the iron, we put more heat from our hand into the iron than we would into the wood. This would be smaller than this one. I don't know if I'm barking up the wrong tree or not. Q would be greater than. Actually, something that feels colder is a greater change in temperature, so that's not going to work. If this feels colder, then the delta T for the iron, delta T change in temperature for the iron is greater than change in temperature for the wood. That makes more sense. When you feel when something feels colder, the temperature changes more. Okay. So the temperature change of the steel is greater than it is for the wood. All right, in order for that to happen, if the same amount of heat is transferred, if these are equal and these masses are equal, then the difference between these two is the difference here. So since these are products, remember a product of, let's use Boyle's law, pressure times volume. Product of two variables equals a constant, then they're inversely proportional. So if we say, we take this one out of the picture here, and we say Q is the same for both of them, then they're equal to each other. Then if the temperature change of iron is greater than it is for wood, then the specific heat of iron must be less than that of the wood, because they're inversely proportional. So which one fits that one? Specific heat capacity of steel is lower than the specific. That's B. Yeah. I mean, that can twist your head around, I'm sure. But, and the only way I can explain it is with math, symbolic math. I guess technically that's algebra. All right. What have I got? 10 more minutes? Yeah. 12 more minutes. Let's see how far we can get. What's this reaction? Okay, we're burning ethanol again. When a 21.1 gram sample of ethyl alcohol is burned, how much energy is released as heat? All right, this is a stoichiometry problem with energy involved. So we'll do this one. So we've got this C2H5OH, which is ethanol, and oxygen yields carbon dioxide and water. And let's see, the coefficients are 3, 2, 3, and 1. And the delta H is negative 1.37 times 10 to the third kilojoules for that reaction. So it's this many kilojoules per mole of ethanol, or this many kilojoules per 3 moles of oxygen, and so forth. 21.1 gram. Okay. We want to know how much energy is released. So this would be per mole of ethanol. That's my abbreviation for ethanol. We need to find out how many moles this is. And I think it gave us the molar mass, didn't it? 4607. All right, this has to go in the denominator to cancel that. So we divide 4607 into 21.1, be less than 0.5. It's 0.458 moles. Okay. So now all we have to do is multiply that 0.458 moles of ethanol, right? Cancels this term and leaves us with energy term. It's a negative 627 kilojoules. Is our answer in kilojoules? Wait a minute. No, our answer is in. Wait a minute. Yeah, okay. All right. It's they left off the negative sign because the question asks how much energy is released. And that's this part right here. So they left that off since the question was asking for how much is released. 627, which is 6.27 times 10 to the second kilojoules. Okay. All right. Let's see, 45. The total volume of hydrogen gas needed to fill the Hindenburg was 2.1 times 10 to the 8th liters at 1 atmosphere and 24.7. How much energy was evolved when it burned? All right. We would do a similar calculation here. What we need is the moles, that liters of hydrogen. So I'm gonna tell you how to solve it. So you need to use ideal gas equation. And you need to come up with how many moles of gas. So do we have pressure? Yep, we got pressure, 1 atmosphere. Volume, liters, 2.11 times 10 to the 8th liters. And R is 0.08206. And temperature is 24.7 plus 273. Solve for N, that gives you the number of moles. And since this equation is written in terms of 1 mole of hydrogen, 1 mole of hydrogen, then it's minus 286 kilojoules per mole of hydrogen. And you just take this value, multiply it by that, and you got your answer. Okay. And you should come out with 2.47 times 10 to the 9th kilojoules. That's a lot of energy. All right. So when everybody's seen the film of the Hindenburg crash. When you see that thing going up in flames, I mean, that's no accident. Well, it was an accident, wasn't it? We think. There are some conspiracy theorists who think it was set, but it was probably just a spark. Right? Hydrogen's dangerous to work with. Now, the Germans had to work with hydrogen because we embargoed their helium from World War I. Helium was considered a strategic reserve. So the America had the world's supply, essentially, of helium because we had all the gas wells, and that's where helium comes from. We take the helium out of the natural gas we pull out of the ground and send it back into salt domes in Louisiana and Arkansas, maybe in Texas too, and store it, right? It's still there. We're drawing from that, and we get some, of course, when natural gas comes out of the ground. But it was a strategic element, and we embargoed Germany. So they had to go to hydrogen. Now, hydrogen has a greater lifting power, right, than helium does, but it's also more dangerous. All right. Hey, what? What energy change occurs when 1.2 moles? All right, this is very simple. Right, you can do that calculation. Right, you just have to find out how many. Well, we got moles of methane. Right, for every mole of methane, minus 434 kilojoules is released. So 1.2 times 434 kilojoules, and then change that to joules, and you'll get your answer. Right? Energy released, because it's a negative delta H. I'm trying to hurry through. So consider the following specific heats of metals. We're given specific heats for each one. If the same amount of heat is added to 25 grams of each of the metals, which are all at the same initial temperature, which metal will have the highest temperature? All right. So let's look at it from this standpoint. Equals S for the metal, right, times its mass, times the change in temperature. So let's change that to temperature final minus temperature initial, since the initial temperatures are all the same. So the same amount of heat is going to be added to each one. This is a constant. All right. And is the mass the constant? 25 grams of each. Yes. So this is 25 grams. Okay. And this is the same. So that's a constant, that's a constant, that's a constant. The only two that change are this one and that one, depending on the metal and the final temperature. Okay, so notice that these are products. This is a variable times that variable equals a constant. And remember what happens if you have two variables, like Boyle's law. If you have two variables times a constant and they multiply together, then they're inversely proportional. Right? So, let's see, which metal will have the highest temperature? If we want this one to go up, that one has to go down. So the one with the smallest specific heat will be the highest temperature. And that will be, looks like, let's see, lead 0.127. Lead will be the highest temperature. Right, 51. Let's see who's next. We'll skip these ABCs and get down to this one. Here we go. Number 59. We've got 4 reactions here, each with its own enthalpy. And we want to calculate the standard enthalpy for this target equation, P4O10, P4O10 plus PCl5, 6 PCl5, right? Yields 10 Cl3PO. Oop, that's a gas, sorry. 10 Cl3 PO. That's a gas. Okay, that's our target. We want to calculate the delta H for this reaction. So we're going to use Hess's law and combine these component reactions in order to reach this one, and then combine the delta H's. Okay, so let's look at P4O10. Which one of those has P4O10 in it? Roman numeral 2 has P4O10. But it needs to be reversed. So what happens to the delta H when you reverse it? You change the sign. So P4O10 solid yields P4 and 5O2. P4 plus 5O2. All right, we've got the same amount here and here. We just had to change the sign, which is 2,967.3. And that should be kilojoules. That's a positive now. Okay, we've used the 2. Okay, how about PCl5? Who's got PCl5? It looks like number 3, Roman numeral 3. PCl5 is on the left-hand side. It's on the right-hand side there, so we need to move it on the left-hand side. PCl5. And that yields PCl3 gas plus chlorine. Yeah. Now, since we had to flip it, we changed the sign. So it should be plus 84.2. The problem is we need 6 of these. right? So we multiply this times 6. And this also times 6. $84.2 times 6 is 505.2 kilojoules. So we're going to use this one. We're going to use this one. And this becomes 6 here, 6 here, and 6 there. Okay? So that's taking care of this one, that one. Now we need Cl3PO. Who's got Cl3PO? Roman numeral 4. Okay? It's on the correct side. PCl3 gas. PCl3 gas plus 1/2 O2 gas yields Cl3PO gas. Okay, that value stays the same, minus 285.7. The problem is we need 10 of these. Let's see. We're gonna need a little more room there. So we multiply 10 times that and 10 times this one. So that's minus 2,857 kilojoules. And this becomes 10. This becomes half of that. And this becomes 10. Now we got that one and that one covered. Okay. So what did we do in the process? Well, this one stays. This one stays. This one stays. What about the others? Well, we got 502 here and 502 on the other side. Those cancel. We got PCl3 on this side, 10 of them, and we got 6 on that side. So that cancels those and leaves us with 4 PCl3s. Okay, keep that one, we keep that one. How about P4? Cl2 and P4. So we got to do something with that one and with that one and with the rest of these. Okay, so do we have one that'll work for that? It looks like number 1 has PCl3 on the right, which is where it needs to be. PCl3 on the right. The reason it needs to be on the right is so that we can cancel that one. Okay, how about on the left? We have a P4, and this is Roman numeral 1. P4 solid plus 6 Cl2. Okay, so this one cancels here. P4 cancels, left side, right side, and 6 Cl2 cancels. And we didn't change anything, so we keep the same number, minus 1,225. 0.6 kilojoules. Okay, so those in the boxes are the ones we want to add up to find out what our delta H is for the target reaction. So let's see, 2967.3, 505.2, and minus 2857, and minus 1225.6. And I get minus 610.1. minus 610.1 kilojoules. Right. And that's B. I know that was a lot of work, but if we be methodical about it, then we can keep ourselves out of trouble. All right, who's next? Skip a few. Go down to 68. All right, choose the correct equation for the standard enthalpy of formation of CO, where delta H of formation for CO is minus 110.5 kilojoules per mole. GR indicates graphite. Okay, this tests whether you remember how to write a formula, an equation for the formation of any compound. And when you do that, the equation for standard enthalpy of formation, you start with the product, and the product is the compound. So we start with carbon monoxide gas. Okay. Then we take each element in that compound and write it as reactants. And it needs to be the most stable form of the element under standard conditions. So carbon is going to be graphite, one carbon, and oxygen is most stable as the diatomic. So that's oxygen gas. And we only need one of them. So here it's permitted to use fractional coefficients. Okay? So that's carbon graphite, 1/2 oxygen, you use carbon monoxide, which is, it looks like C. And of course, delta H is given to you already. Delta H is minus 110.5. All right. Who's next? Let's see, skip a few. 78. One of the main advantages of hydrogen as a fuel is that hydrogen as a fuel, what does that mean? If we use hydrogen as a fuel, we could say we combust it. Yeah. If we use hydrogen as a fuel, that means we're combusting hydrogen in an oxygen atmosphere. And the only product is water. Okay. So if we wanted to balance this one, it'd be 2 there and 2 here. To answer this one, the main advantage is that the only byproduct, the only product of the combustion is water. That's A. It doesn't contain particularly large amount of energy per unit volume. Right? Plants cannot economically produce hydrogen. That has to be made by a laboratory tested industrial process, such as electrolysis of water. It can economically be supplied by the world's oceans. Well, at the present time, no. Because in order to provide an economical source of hydrogen from the oceans, you need a cheap source of energy. Most of the world is dependent upon fossil fuels right now. And it's more efficient to just refine the fossil fuels into gasoline or diesel. That's cheaper than it is to produce hydrogen from water. But if we had a cheap source of energy, like nuclear energy is relatively cheap, absent the regulations and all the other garbage that's laid on the industry, you could produce hydrogen very cheaply. So the main advantage of hydrogen is that it only produces water as a product. Let's see, 79. Which of the following is not being considered as an energy source for the future? All right. In order to provide a source of energy, you either have to be able to combust the product, or you've got to get at its nucleus. But if it's already at a low energy state, then it's not good as a fuel source. Ethanol, methanol, oils of any kind, seed oil, shale oil, those all have stored energy in their chemical bonds. Carbon dioxide does not have energy available. Now, a more complete explanation for why carbon dioxide is not a good candidate for energy will come, let's see, when will it come? Second semester, I think. Yeah, second semester when we talk about oxidation states. But for now, just know that carbon dioxide is a product of energy use, not the reactant. So carbon dioxide is not a good source of energy. All right, we'll skip a few more. And number 90. A gas absorbs 188 joules of heat and then performs 310 joules of work. Change in internal energy of the gas is. All right. So the definition for internal energy is the summation of heat and work. So if a gas absorbs energy, the gas is the system. And then everything else is the surroundings within those boundaries. So if it absorbs heat from the surroundings, the value is going to be positive, 188 joules of heat. If the gas does work on its surroundings, then this is Q, this is W. Right? So the W is going to be negative 310. Okay, so the change in internal energy would be, let's see, 2, 2, 1. Negative. That'd be 10, 1 and 10. 1 and then 1. Yeah, that's right. 122 joules. Minus 122 joules is the change in internal energy for this process. Okay, there's a lot of repetition in there. Let's see about this one. Number 99. This word problem has a lot of fluff in it. Nitric acid was first prepared 1,200 years ago by heating naturally occurring sodium nitrate with sulfuric acid to produce sodium bisulfate and collecting the vapors of hydrogen nitrate. So the reaction itself produces a gas of hydrogen nitrate, and you collect it in water, and that's nitric acid. Okay, we want to calculate the delta H for this reaction using the heat of formation. So the balanced equation is sodium nitrate. Sometimes the phase matters, so we have to include the phase. Sodium nitrate, H2SO4, liquid, yields sodium bisulfate or sodium hydrogen sulfate, solid, plus HNO3 gas. Now let's see, is that balanced? One sodium, one nitrate, two hydrogens, one sulfate. That's a balanced equation. So how do we calculate the delta H for this reaction? We sum up the heats of formation, right, of all the reactants. Excuse me, products. Times the number of moles of each. Each one is 1, so N is going to be 1 for each one. And then we subtract the reactants. This should be, excuse me, this should be delta H 0 for the products formation. And this should be delta H formation for the reactants. Okay, so the products, sodium bisulfate. Sodium bisulfate is minus 1125.5. Minus 1125.5 kilojoules. And since there's the coefficients are 1 for each one, then it's just that kilojoules per mole. And then the second one is HNO3, which is minus 135.1, minus 135.1 kilojoules. Then we subtract the summation of the reactants. Sodium nitrate, minus 467.8 kilojoules. And then, let's see, H2SO4, minus 814.0. So we just change that to a minus. There we go. So the delta H 0 for this reaction will be, let's see, let's do this one first because a negative times a negative is positive. So we'll say 467.8 plus 814. This is 1281.8 kilojoules. Positive. And then this one is going to be negative. 1125.5. And then 135.1. So I get, well, I went ahead and added them all up. So combined all of these. Like, this is combination of that one, and I went ahead and subtracted these from that one. And I get 212 kilojoules. Oh, it's 21.2, sorry. Forgot my decimal point. 21.2 kilojoules per mole. And this is a positive value, which means this reaction is endothermic. You have to add heat to it. Okay? So that's C. Okay. Here's next. Oh, that's it.